Okay, good morning. It's August 15, 2023. The time is around 1:37 a.m. Los Angeles time. This is Professor David J. Delosreyes. Okay, my topic for this morning will be a long video format discussion, and the topic will be with regards to alternating current circuit, and this will now be lesson number 20. Lesson number 20. So we are now through with the study of impedances. Okay, we now know series impedances. We now know parallel impedances. We now know how to compute if the given circuit is series parallel combination impedances. We now know how to compute apparent power, true power, reactive power, what call this power factor, and some other things. So we will now proceed with the so-called, uh, it will be solutions on how to compute a current, okay, authored by the, what you call this, wise people on the study of electricity. And one of the topic is actually Thevenin's theorem. Thevenin's theorem is actually a theorem which simplifies an active network into a simple network, in which if the current going to the load is being asked, okay, will make the solution simpler. Okay, let's proceed. The last lesson for this morning under alternating current circuit will be AC circuit lesson number 20, and this will now be Thevenin's theorem. Thevenin's is a family name, and he invented a theorem on how to compute the current consumption of a load if this load is to be connected to a given active network. And we do not know anything on that active network, the one inside. There should be some voltage sources, there should be some impedances, but we do not know the nature of that one. So Mr. Thevenin actually simplify this active network into something like this. Okay, what he did is that he just make a power source ETH and CTH connected in series with the load in which the current passing through it is being asked. So the main motive of the Thevenin theorem is actually on how to compute the current to a given load, okay, if it is connected to a given active network. The problem is, what will be the current passing through this with this given active network, okay, but we do not know anything about it inside, right? Okay, I will try to read what is Thevenin's theorem, then I will try to explain it as concise as possible so we could understand it in the so-called layman's way. Okay, Thevenin's theorem. Thevenin's theorem is termed to as the so-called constant voltage source. Okay, I will try to read it. Any two-terminal network of fixed impedances and sources of EMF can be replaced by a single source of EMF, and that single source of EMF is termed to as the so-called constant voltage source, whose voltage is equal to the voltage across the terminals of the network, and having in series an impedance looking back into the network from the two terminals, with all the sources of EMF replaced by their internal impedances. It is quite long, and actually we could summarize this one by bringing out this procedure. So meaning to say, if we are given a complex active network, okay, and we are to connect a load CL across it, initially that load is not connected, right? And we try to connect that load. And the problem is asking what will be the current that will pass through this load CL here, and we do not know anything about that active network inside. So Mr. Thevenin did something on how we will know the parameters inside the active network. What is the voltage source inside? What are the impedances inside? Okay, let's try to bring out the procedure on how to take the Thevenin's equivalent of any active network. Okay, number one, solve for E with the subscript TH. TH is Thevenin's. It is shortened to just simply TH. So solve for E with the subscript TH. ETH is the equivalent open circuit voltage. Hold on, I am taking my multimeter. I am bringing out my multimeter. So, procedure number one, what Mr. Thevenin did is that he got his multitester and he will try to measure the voltage across the terminals. He doesn't know anything about the inside of the active network. Is the voltage source inside DC or is the voltage source inside an alternating current circuit voltage? So he uses a multimeter to measure the voltage. So it will come out if it is an AC voltage or DC voltage. And according to him, what you can measure here is actually ETH, the Thevenin's voltage. The equivalent open circuit voltage. Open circuit meaning there's no load yet connected, right? So he just stopped the voltmeter over here and he computed or measured that ETH, that is E with the subscript TH, okay, meaning the Thevenin's voltage. The open circuit voltage that will come out here. Okay, that's number one. And number two, solve for CTH, capital Z with the subscript TH, meaning impedance TH. This is Thevenin's impedance, the available open circuit impedance. It seems like you set your tester to the ohmage thing, okay? Then try to measure the open circuit impedance over here, okay? And Mr. Thevenin termed to that one as simply CTH. Okay? Number three. So he's discovering something, right? By using the multitester, he measures ETH. Then he measures CTH, right? Number three, draw the Thevenin's equivalent circuit of ETH in series with CTH and reconnect CL. It is something like this. It is the load is not yet connected, right? So according to procedure number three, after computing for ETH and solving also for CTH by using the multitester, right? Mr. Thevenin said that whatever the voltage that come out, it should be connected in series with that CTH. Okay? And then he tried to reconnect the unload, reconnect. Right? They reconnected. So what comes out after the reconnection, okay? What kind of circuit is that one? We got a voltage source, we got the Thevenin's impedance, that's from procedure number two. We got CL, okay? CL is actually the impedance load that should be connected in here, in which we are looking for the current passing through it, just in case we connect it to the given active network, right? So after the reconnection, CTH and CL are actually in series. So this will now be an AC money or AC procedure if the problem is asking for the current passing through the load. Because, oh sorry for this one. For AC circuit, voltage is equal to IC, right? Voltage is equal to IC. So we can use this formula here, solving for current now. We divide both sides by I, right? By I. Or Z rather, right? Z. Okay? So I now will be voltage over impedance. So this voltage is the ETH and the total impedance. Since they are in series, it should be the sum of CTH and CL vectorially. We are considering for the mean time AC circuit. So the unknown load current using the Thevenin's theorem will be what comes out for ETH using procedure number 1 plus the vector sum of CTH coming from procedure number 2 plus the load that is connected to the terminal. Okay? So, number 4, that's what I've done. Number 4, procedure number 4, IL now is the ratio of ETH and the vector sum of CTH and CL. Meaning, the vector sum of CTH and CL, if we divide that to the value ETH, that will be the unknown current, okay, passing through the load CL. As simple as that one. Oh, that's Thevenin's theorem, okay? That will be the very concise explanation of the Thevenin's theorem. If we are asking, if the problem is asking for the load passing through this CL here, if we try to reconnect on the given active network, right? The problem is just asking what will be IL if we try to reconnect here and we do not know anything what's inside. That's why Mr. Thevenin discovered a theorem in which we will know the components inside. Components meaning what will be the equivalent voltage source inside and what will be the total impedance that will come out inside. That will affect the current passing through CL. Okay? Okay, that's Thevenin's theorem. That's a simplified solution on how to bring out the current passing through a load CL if we are given an active network. So, Mr. Thevenin, I will repeat it before we will go for this morning. Solve for ETH, okay? He will solve the voltage across this. Then he will solve for the value of CTH across this. And after taking the value of ETH and CTH, draw the Thevenin's equivalent circuit, and it will just be simply a series circuit. The Thevenin's voltage is in series with the Thevenin's impedance, and if we try to reconnect the load across the terminal, what comes out now will be two series impedances. So to compute for the current passing through this load, the main concentration of the problem is on the computation of the current that will be drawn by the load, right? That is just the main concentration. Okay, we just make it simple so we could understand it. So IL now will be this voltage here divided by this vectorial sum of CTH and CL. Okay, there is a note on the computation of CTH. CTH is computed using the concepts of series and parallel impedances. What I did is that by using the voltmeter and the ohmmeter in the computation of ETH and CTH. But if we are solving problems paper-wise, okay, on the board or right in our computer, we will be using our knowledge of the so-called study of the concepts of series and parallel impedances. So in the computation of the impedance, use the knowledge of the concepts of series and parallel impedances. Okay, with this multi-tester, actually we cannot compute, we cannot measure impedance over here. I'm just telling you that it seems Mr. Thevenin, to compute for CTS, he will get the impedance over here. But in actuality, that a CTS actually is computed by using the series and parallel impedances concepts. Okay? For the voltage, we could do it, right? But for the impedance, we cannot measure impedance by using the multi-tester. But for the voltage, we could measure the multi-tester. So the ETH could be known by using the multi-tester. But for the impedance, okay, in actuality, in real life, okay, the computation of this is actually by using our knowledge of the concepts of series and parallel impedances. Okay, that's it, guys. So for those of you who are taking up electrical engineering, this is for you guys, right? If you want to subscribe to my channel is at youtube.com/@ProfDavidJDelosReyes. If you want to share it, please click share. Okay. Good morning from Los Angeles. This is Professor DavidJDelosReyes. Lesson number 31, okay, or 21. I will be giving you example problem on Thevenin's theorem so we could visualize the four procedures here, right? So you will know on how to apply procedures number 1, 2, 3, and 4 by using Thevenin's theorem. What I discussed tonight is just the concept. Okay, so to better understand the concept, the next time around, I will be giving a problem on how to implement procedures number 1 up to 4 using Thevenin's theorem in the computation of the current passing through the load CL. Okay, good morning from Los Angeles, Professor DavidJDelosReyes.